So cellular respiration is where we take glucose, oxygen, and it's converted into water, carbon dioxide, and chemical energy. The chemical energy that is used, we can put that meter stick, we don't need it, that's for my physics class. Thank you for setting it down. I know you did not originally have it. Chemical energy is in the form of ATP. The chemical energy that your cells need and use is ATP. Our body, as an organism, we need sugars, glucose, but our cells don't directly use the glucose for movement, for their whatever functions they are. They use different form of chemical energy, ATP. So cellular respiration converts glucose into ATP. And ATP stands for adenosine triphosphate. And what happens is adenosine triphosphate, when our cells use it, is converted from ATP to ADP, adenosine diphosphate. So we go from a three phosphates, to a diphosphate, 2 phosphates. So we break a bond in the phosphate, we release chemical energy, and now we have diphosphate. I like the analogy that I've seen before of ATP is like your cell phone battery or your iPad battery. In order for your iPad to work, we have to convert some electrical energy from the outlet and charge it, right? We have to put some energy in. That's what the glucose is, putting energy into that ATP bond. But then what happens is we use our device and we use some of that energy. Our battery is now, our iPad turned off because my battery is low. Does that battery still have some energy in it? Yes, it does. It's just not enough to run your device. ADP still has some energy in it, it's just not enough to do the cellular processes. So we have to then charge that ADP back to ATP, and we charge it with glucose through the process of cellular respiration. Now in this diagram, and a lot of diagrams we see, it says that cellular respiration occurs in the mitochondria. Realize that is not a 100% correct statement, and I mentioned that yesterday. 2 out of the 3 steps occur in the mitochondria, but it also occurs in the cytoplasm. So cellular respiration occurs in the cytoplasm and the mitochondria, and during that process it releases carbon dioxide and water. And then photosynthesis uses the carbon dioxide and the water and some light to produce oxygen and glucose, which then is used in cellular respiration. All living things go through cellular respiration. All living things go through cellular respiration. Some organisms go through the photosynthesis, but all go through cellular respiration. All living things need oxygen and glucose in order to live and survive. Some organisms just happen to make their own oxygen and their own glucose. We can leave that down. So when we talk about this, the fact is these 2 chemical reactions are really close, but they're exact. Okay, they are not exact opposites of one another, but they're very similar. So if you know what the reactants of one of these chemical reactions are, those are your products of the other. You know the products of the one, you know the reactants of the other. The difference comes in the form of energy, and in photosynthesis, our reactant, it needs energy in the form of sunlight. And in cellular respiration, it releases energy, and it releases it in the form of ATP. Okay, it's a different form of energy. So the types of energy are also different. All organisms go through not all organisms go through photosynthesis, but all organisms go through cellular respiration. Okay, and I mentioned that already a couple times. Photosynthesis occurs in the chloroplast, found in plants, algae, and some bacteria. Cellular respiration occurs in the mitochondria and the cytoplasm. And then photosynthesis only happens when there's daylight, whereas cellular respiration happens all the time. Even when you're sleeping, cellular respiration is occurring. Some people have a higher rate of cellular respiration than others. Right now you're going through cellular respiration, and some of your cellular respiration rates are higher than others. We generally refer to that as metabolism. So metabolism is just kind of the total amount of cellular respiration that occurs on a given amount of time. So if you're just sitting there, you might be doing cellular respiration and making up a number 10 times, where the person next to you might be doing it 15 times, which means if you eat the same amount of food, they're going to use that food up quicker. Okay? So when they talk about metabolism, that's kind of what they're talking about. But it happens all the time. Even when you're sleeping, now your metabolic rate decreases when you sleep. You don't break down this food as frequently when you sleep because a lot of your cellular processes also slow down. Your breathing rate slows down. You're not moving your arms all over the place. You're not walking. So a lot of what the energy demands are much, much less. Okay, again, the ultimate goal is to slowly release energy to maximize the ATP output. The example I used yesterday was the tank of gas, and I like it from the standpoint of if I have a whole tank of gas and I slowly release that energy, I can get a couple 100 miles down the road, I can get a couple hours down the road. I can slowly release that energy and I can get a couple hours or 100 miles down, a couple 100 miles down the road. However, if I were to release all that energy of a gas tank all at once with a big explosion, lots of energy is released in a very short period of time, and your car would move. It would just move in little tiny pieces in all directions. And it wouldn't get you hours down the road. It'd take a couple seconds to go a couple feet because of the explosion. Cellular respiration, slow release of that energy to get us so we don't have to constantly be eating food. Okay, we don't have to constantly be inputting all of that food. Okay, and this is kind of all that same stuff again. All organisms go through cellular respiration, some go through photosynthesis. So the difference between the types of cellular respiration come down to two basic kind of categories. Plenty of oxygen or lacking oxygen. And we call that aerobic versus anaerobic respiration. So cellular respiration occurs in the cytoplasm of the mitochondria. And if there's an absence of oxygen or there's not enough oxygen present, we call it anaerobic respiration. You're starving for oxygen, anaerobic. If there's enough oxygen, we refer to that as aerobic respiration. Now, big picture, anaerobic, no oxygen, small amount of ATP. We often cite 2. Aerobic respiration, when there's plenty of oxygen, lots of ATPs compared to anaerobic. And the number often cited is 36. Now that 36 is actually not a definite number. Sometimes we'll see 32, sometimes we'll see 40, sometimes we'll see 38. And it varies from publication to publication, and I believe it also varies within parts of your body. So maybe some of your muscle cells are going to have a higher ATP output than some of your other cells. The big difference, and something I expect you to know, is anaerobic has a small amount of ATP release, where aerobic is a lot compared to that too. So a better written multiple choice question by a teacher would be, how much ATP is produced during anaerobic respiration? It's in the 30s, so a decently well written multiple choice question would be, how many ATPs are released during aerobic respiration? 34, 2, 10, 12. Now you can say, well, you didn't say 36. You're right, but that's a range. 36 is not a steadfast number. So a better written choice is like, well, I know that ATP has a lot. All right, a lot of ATPs is produced during aerobic, and it's in the 30s, so I should choose the one that's like 34. A teacher who would write something along the line, which of the following is it 31, 32, 33, or 2? That's not a good multiple choice question, because that's getting pretty nitpicky, and it's not an exact number, it's a range. So realizing a question like that, I'm looking for it's about 18 times more ATPs. It's in the 30s, but it's definitely not 2. Okay, that's definitely not a 2. Anaerobic, however, that's huge, only produces 2 ATPs. It only produces 2 ATPs without enough oxygen present. So we can do both. We can do both of these. We are much better and much more efficient during aerobic respiration than anaerobic respiration. I'll give you an example of an aerobic activity that you do sitting in biology class at your desk. That is an aerobic activity. You have plenty of oxygen sitting there doing what you're doing right now. In fact, you have enough oxygen that you breathe in some oxygen and you don't even use it all, and when you exhale, you breathe some oxygen back out. That's why mouth-to-mouth resuscitation works, just for the record. You have enough oxygen in your breath that you exhale for the person that you're breathing it into. You have an excess of oxygen. Yeah, that was funny. Okay? So, aerobic respiration, or an aerobic activity, would be sitting in your desk in biology class. Walking down the hall to the lunchroom would be an aerobic activity. You have plenty of oxygen when you walk down the hall to get lunch. Well, that's... What would be another aerobic activity that you're not lacking oxygen when you do it? What's something that you do that you have plenty of oxygen during that activity? There's lots of them, just for the record. What's that? Sleeping, yeah. Unless you have sleep apnea, they use like stop breathing for periods of time, and then you kind of like a gasp because you're actually like depriving your brain of oxygen for a short period of time. I think that's what sleep apnea is. I might not have the exact definition right, but I know it's when you stop breathing for a period of time. But generally, we'll say in the general statement, yeah, sleeping is an aerobic activity. There's plenty of oxygen available when you sleep. And your breathing rate is relatively normal. Actually, it's slightly decreased because you're just laying there. You're not even, like, you're doing like pretty much nothing. What else? About in gym class. Hi, sorry. Oh. I almost said a bad word. I almost called it gym class. Sorry. Sorry, Phi Ed teachers. Don't tell them I said that. I almost screwed that up. Phi Ed, physical education class. If you were going to run the 12-minute run, is that an aerobic or an anaerobic activity? Let's say in the first 3 minutes of that. It's aerobic, right? Because yes, does your breathing rate increase? Yes, but you still have enough oxygen that you're able to maintain. Ideally, 11 minutes in, you're still also aerobic. If you want to get that little bit extra right at the very end, then you might go anaerobic, right? 30 seconds left. Then you might go anaerobic. But a long distance run needs to be aerobic because you can't perform a long distance run anaerobically. It's not efficient enough. Your body would physically collapse because you would become energy deficient and your legs would give out. Okay, so those are some examples of aerobic respiration. An example of an aerobic, sorry, I keep saying it, anaerobic activity, the best one I can think of is a sprint. Okay, so I can sprint as fast and as hard as I can for a short period of time. I can go slightly oxygen deficient for a couple of seconds, and I can be okay. It won't be very efficient. I'm only producing 2 instead of 36, but I can do it for a couple seconds, and I'll be okay. I'll be tired, but I'll be able to make it. So I often talk about like 100-meter dash. I can go and I can run a 100-meter dash. I'm right back in high school. I think I was right around the 7-second mark, something like that. No, not 7 seconds. Oh. Oh, yeah. No, isn't it? I thought it was. That's good time, isn't it? That's a good time, I think. For the record, I said the 6 seconds in my second hour class, and someone emailed me and said, "Congratulations, you're faster than Usain Bolt." So, yeah. I mean, when I was in high school, I did clarify that when I was in high school, a little better shape than. So, okay, let's go 10 seconds. Because see, I think he was like 958, something like that. Is this 100 meter record or something like that? So, let's go 10 seconds. Now that's so we've 10, let's just go 10 seconds. Let's pretend I'm almost as good as Usain Bolt. Almost. And I can run a 100 meter dash in 10 seconds. We all know that's not true, but whatever. But I can go and sprint as hard as I can, as fast as I can, and I can do it for about 10 seconds, and I'd be okay. Could I do that same exertion of energy for a 400 meter dash? Could I run as hard as I can for all the way around the track once? Or do we kind of have to pace ourselves slightly on a 400? Slightly, right? And the better you are, the faster and the harder you can go, right? But I can't run 400 at the same pace that I run a 100. What would happen physically to me if I tried? What would happen?
You would fall over.
I would fall over because I don't have enough strength to hold my legs up because I become so energy deficient. I'd run and run and run. Now let's talk about psychology of an athlete just for a moment. Psychologically, my mind would stop me before that. And we could talk about that's the difference between like Olympic caliber athlete and a good athlete is what their body and their minds kind of talk. Because our bodies are capable of more typically than our brains let us do. Okay? I might try to sprint that 400 and I might get 120 meters down the track and be like, I can't do this anymore. And my brain wants to shut me down. But in reality, maybe my body can make it 200. But my mind is going to tell me, like, you can't go anymore. You need to conserve. You need to stop. Preservation kind of thing. So there's some psychological thing there. But that's a different conversation. That's a different conversation, okay? So sprinting is one that I often talk about that we go through in anaerobic. We can do it for maybe 10 seconds, but I can't do it for 10 minutes, okay? Anaerobic respiration is relatively inefficient, but it is something we can do for short periods of time. If you personally were to go anaerobic, there's two types of anaerobic respirations that could occur, but only one of them occurs in humans. On the screen it talks about lactic acid fermentation and alcoholic fermentation. You, as a human, go through lactic acid fermentation. Lactic acid fermentation is what our bodies go through. Our bodies do not go through alcoholic fermentation. We go through lactic, but some organisms do. So once upon a time, I don't know if this is still the current philosophy, but I remember when I was in physical education class in the junior high, they talked about when you run the mile, make sure you walk afterwards, otherwise you're going to get that sore muscleness, and it's because lactic acid is building up in your muscles. I don't know if that's current science. I don't think it is. I think that has to do with something else. It's not just lactic acid. I think there's more to it than that. But we go through lactic acid fermentation. Alcoholic fermentation is what other organisms go through. Yeast is the classic example of alcoholic fermentation. Yeast is a microorganism. It's a living thing. That powdered stuff that you put in your bread is actually a living organism. And it needs certain conditions in order for it to work and for it to live. So it can go dormant in the fridge, but in order for it to get activated or to become effective, it needs certain conditions. So when we talk about yeast, yeast goes through alcoholic fermentation. It's an anaerobic respiration, and we often will go through and we'll put yeast in bread, for example. Why do we put yeast in bread? Come on, why do we put yeast in bread? So it rises. Which, when we cut in through a slice of bread, what do we see because it rose? We see air bubbles or air pockets, right? So when we add yeast to bread, yeast eats, breaks down sugars, and it breaks down these sugars and it changes the type of sugars, changes the flavor. So bread tastes different based upon what sugars are broken down. But what happens is it takes sugars And if there's not enough oxygen, then it goes through alcoholic fermentation, and those bubbles that we get in our bread that make it rise are carbon dioxide. Now, I don't know how many of you have ever made some type of bread, pizza dough, something like that. A lot of times you'll need it. I have a bread machine that does this for me. I push a couple buttons. Bless you. But the idea is it mixes that yeast into the dough, the sugar, the water, and oil. That's what mine is. Depends on what kind of bread, I guess. And it'll break it down. And part it'll rise, and then if you're kneading it by hand, you punch it down generally, and you pop those bubbles. My bread machine starts moving again. But then you knead it some more. And the idea is you pop those bubbles, and then you let it rise again, and you do that. And the idea by doing that a couple times, it gives it longer time for the flavors to change, more time for fermentation to change. And if you didn't do that, it kind of gets this big balloony thing, and then it might run out of space. So you punch it down. But you kind of get that smell when you bake bread. It kind of smells, in my opinion, a little bit like beer. And it's because you actually have a little bit of alcohol in the bread that as you bake it is evaporating off. So that kind of smell when it's rising is actually a little bit of alcohol that's being produced. Now, alcohol is the primary reason why yeast is used for beer and wine. And what happens when we ferment beer or we ferment wine is it takes the sugars that we start with and it converts it into ethanol, which if you're making beer or wine, that's your goal, is to make ethanol. So in that process, it converts those sugars and it switches it over into ethanol. And it needs certain conditions, but it converts those and it produces carbon dioxide. Okay, so alcoholic fermentation is something that we do not do, but it is something, it's not something we do in our bodies. Aerobic respiration is what we spend most of our lives doing. It's much more efficient. It can produce about 18 times the energy that anaerobic respiration can do. And it's the most common in plants, animals. All living things go through cellular respiration, and most of them go through aerobic respiration. Okay. Questions about that? We'll spend some time going through, just for the record. And we'll spend some Quizlet time reviewing some terms in terms of cellular respiration, anaerobic versus aerobic. We're working on a graphic organizer, like a flow chart, kind of like we do with photosynthesis. We're also trying to figure out a lab to do over the next couple of days. We're going to test next week, Tuesday. So this activity, this diagram is from an activity we did at the beginning of this unit. Like the very first day of the unit was photosynthesis and cellular and respiration. It was a POGO activity. I never talked about it, and I need to spend a little bit of time talking about it today. So that's what we're going to do with the remainder of class today. So this diagram is very similar to the diagram in your notes, and it shows what comes out and what goes in. Now this diagram I fixed, and I didn't photocopy the fixed one. I like this a little bit better than yours. Yours had a plus sign, and these are smashed together, and there's only one arrow coming out. A diagram like this is something I expect you to be able to label. So on next Tuesday's test, probably going to see something very similar to this. What comes out of photosynthesis, what comes out of cellular respiration. Where do those things that come out of cellular respiration go? Well, they go into photosynthesis, and what comes out of photosynthesis, and where do they go? They go into cellular respiration. The difference is the types of energy. Is it energy coming out of cellular respiration in the form of ATP, or is it energy coming into the chloroplast through the process of photosynthesis? You should know the chemical reactions. You should know that photosynthesis occurs in the chloroplast, that's the organelle, and most of cellular respiration occurs in the mitochondria. Those are some things you should know, and you should expect to see. There was also this diagram that I want to spend some time talking about as well. So this is the carbon cycle. And when we talk about carbon cycles, one of the biggest things we talk about when we talk about the carbon cycle is that atmospheric carbon dioxide, the bubble on the top. In the last decade or so, in science classes, when we talk about gases in the atmosphere, carbon dioxide is a big one. And it's something we really kind of start talking more and more about because with more evidence and more scientific studies, we're finding that that carbon dioxide thing is a big thing. Now, when we talk about carbon dioxide in our atmosphere, it's one of the greenhouse gases. It's one of the greenhouse gases we have in our atmosphere. And a greenhouse gas is a type of gas that allows heat to come in, but it doesn't prevent it from leaving. Is that good or bad? Or both? It's bad in some respects. It's good in some respects. So it's both. It is both. Why is it bad? Okay, let's start with it. Why is it good? You guys ever watch the movie Martian? No?
Yeah.
Couple, okay. Anybody know what temperatures happen, what happens to the temperatures on Mars throughout the course of a day? Night versus day? It's pretty similar, they're pretty drastic.
Isn't it freezing like at night?
It's really, really, really cold, and then it gets pretty warm at night. So they're pretty big temperature swings. Same thing happens on the moon too. And the reason for, I said that the moon, I don't know if the moon gets super hot now that I say that. It doesn't have an atmosphere though. So what happens is that solar radiation comes in, it heats up Mars, but then at night there's nothing to keep it in, so it gets really, really cold. So greenhouse gases are good in the sense as it keeps our temperatures relatively constant, okay? We get fluctuations day and night, like especially in the winter. Hey, it got up to 28 degrees, we're supposed to hit 40 I think today, it was 40 something, but it's 20 something this morning. So we got a 20-degree temperature swing, but if we didn't have an atmosphere, we might get like 300-degree temperature swings. I'm making that number up, but they're pretty big. So greenhouse gases are good for that sense, but they're also bad because if we keep trapping it, as we trap more and more, we get an overall increase in temperatures throughout it. So the reason why we in science classes emphasize carbon dioxide in terms of greenhouse gases is that's the biggest one that we have an impact on. It's not the worst by any means, and there are national cycles of carbon dioxide that increase and decrease, and you can even look at spring versus summer versus fall versus winter. Carbon dioxide levels change because less photosynthesis, more photosynthesis occurs. But we do a lot of this, auto combustion, fossil fuel burning, and if you look at studies, like NASA has a really nice website, that climate scientists who are actively publishing, most, like 90% of them, say that we are the cause of that carbon dioxide emission change and increase. So when we talk about carbon dioxide in our atmosphere, let's talk about what's going on. So there's this chemical process that takes carbon dioxide from the atmosphere and removes it from the atmosphere and it goes into a plant. What's that chemical process called? Takes carbon dioxide, puts it in the plant. I misspoke slightly there. What's the chemical process called? That's plants use to take carbon dioxide out of the atmosphere and store it in itself. Plants use carbon dioxide in what chemical process? Photosynthesis, right? So plants take carbon dioxide out of the atmosphere and they store it as glucose. That's photosynthesis. What chemical process do plants go through that take that glucose and convert it back into carbon dioxide in the atmosphere? Cellular respiration. Plants go through cellular respiration? Sure do. Do plants need oxygen? Sure do, because they go through cellular respiration. So photosynthesis, cellular respiration. Photosynthesis, cellular respiration. If that was the only thing going on in this world, our carbon dioxide emissions would not change. Actually, they'd go down. Because plants are going to sequester, they're going to absorb, they're going to use carbon dioxide for photosynthesis, and they are going to use some of it during their lifetimes. But there's going to be some left over. There's a surplus that plants use. Now what happens is this bunny comes along and it eats the plant, and it takes this glucose, the carbon found in this glucose molecule, and it eats it, and through what chemical process does it convert it back into carbon dioxide? Cellular respiration. So bunnies also go through cellular respiration, and insert any living animal that eats plant, and that's the bunny here. So they go through cellular respiration. Sometimes this bunny dies. Now sometimes this bunny gets eaten by another organism, and then that organism releases that into carbon dioxide, that food source. But sometimes that bunny lays on the ground and it decomposes by microorganisms or fungi, and it's going to go through cellular respiration and release that too. They also go through cellular respiration as they decay food. Now all of that is a pretty natural cycle, and nothing's really changed. Over the process of a couple million years of dead things, in the right conditions, we can form these things called fossil fuels: coal, natural gas, oil, which we use to make like gas. If the right conditions. It takes a long period of time. Now what happened is those once were living things, hence why we call them fossil fuels. They were once living things. And there was carbon dioxide in the atmosphere prior to them being removed by some vegetation millions of years ago. And now they got buried underneath the dirt. They're no longer floating around the atmosphere. They've been out of the carbon cycle for a couple million years until we dig them up. And then we use them and we burn them. So what chemical process is it where we take carbon fuel, coal, oil, natural gas, and we go through and release carbon dioxide? Combustion, right? We burn stuff. And when we burn stuff, it's a really generic of fuel and oxygen, releases energy in the form of heat and carbon dioxide. Is combustion unique to the last 100 years of humans on Earth? Did we just start burning stuff 100 years ago? No, let's pretend you had a cabin in the 1600s. It's cold out, there's snow outside. How do you keep warm? What's that? So what are you burning? Yeah, right? In the 1600s, were probably, this fuel source is wood. So we were still going through this process. I'm saying 1600s, now I'm not saying it was only wood, but that was probably a pretty common fuel source. But what happens instead of me burning a carbon fuel, a fossil fuel, I'm burning a plant. So this plant removes carbon dioxide, and then it would burn it, we release carbon dioxide. The burning of plants is what we refer to as relatively carbon neutral, because during the life of that plant, it will have removed X amount of carbon dioxide from the atmosphere. It will use some of them through its process of cellular respiration, and then if we burn the tree, we're releasing the rest of it. But it's a net carbon, it's carbon neutral because the amount of carbon it removed is equal to the amount of carbon we just put back in. So that's a relatively carbon neutral. We refer to that kind of burning the thing, we refer to like, what is a renewable resource? Because we can go through, it's not a fossil fuel, didn't take millions of years to form. It took a long time, right? It takes a while for a tree to grow, but it's relatively short timeline. Like during your lifetime, you could plant a tree, and when you're my age, you could cut that tree down and you could burn it to heat your house. And then you could plant a new tree, and then maybe you could burn that next tree before you pass it. Okay, so we call that renewable because it's a relatively short period of time. But what happens, and combustion isn't new, like even naturally, if there's forest fires before people left campfires going, right? Lightning strikes, someone mentioned it, I never thought of it, volcanoes, lava flows could start a forest on fire, which could cause natural forest fires. So combustion was a thing pre-human, us causing them. So there was combustion going on. But what happened, right around the Industrial Revolution, this became much more used, and this process became much more predominant. So what happens is a combination of a couple of things. We are using lots more of this. These have been out of the carbon cycle for a couple million years, and now we're burning a lot of it. Okay, a lot of you drove a car to school or rode a bus or used some form of fossil fuel to get here. And you release carbon dioxide. Some of you walked, which didn't. Then you did this in your walk to school. But what happened in the Industrial Revolution is we started doing a lot more of this. And as we did more of this, we also started probably cutting down more of these. Okay, so with less plants, Why are there less plants? Because I'm going to make housing development in once was a forest. I'm going to cut down the rainforest because I'm going to raise cattle on that spot of land. You know, I'm going to build a school. I'm going to build a road. Stuff like that. So by cutting down trees and plants and destroying plants, there's going to be less photosynthesis, which means we're removing less carbon dioxide from the atmosphere. And we're burning more fossil fuels, so therefore we're removing less and we're adding more. Overall, our numbers are going up. Now, how could we produce electricity? Well, I guess let me start over. What's the #1 way we produce electricity in the United States? Coal. Does anybody know where the closest coal electrical power plant is? So drive from here to, what's that? Yeah, it's over by the Culvers in by Cedar Creek. Okay, Wassa Homes. So if you're going down the highway, you go past, hey look, there's Culvers, and you keep going towards Mosinee, and you see Wassa Homes. Behind Wassa Homes, those big smokestacks, that's a coal power plant. They burn coal. And if you were to take old Business 51 to Mosinee instead of taking the highway, you can see the piles of black coal. So we burn coal right in our backyard. We burn coal. #1 way in the United States we do it is with coal. The Domtar paper mill over by Rothschild Elementary School, about 15 years, I'm making that number up, but probably about 15 years ago, they built a biomass plant. So they produce electricity. They also produce a lot of steam for the paper production process. But instead of burning coal to make that electricity, they burn wood, okay, which is a relatively renewable resource. But they use like the tops of the tree, the bark of the tree that's not actually used in the paper process. So they use some of the byproducts that weren't used before to then produce steam and electricity for that process. Okay, so we are still releasing carbon dioxide, but we're not burning fossil fuels by doing that. What else do we use to produce electricity in the United States? What's that? Solar? Yeah, solar panels, right? You could put some solar panels on your roof. There's no combustion that goes on at all. There's actually no plants involved either. So that's a good way in terms of carbon. Now we got to make the solar panels. There's always that production process. We got to make it first. But we aren't burning anything. So that's good in terms of carbon dioxide. What else?
Turbines.
What kind of turbines? Wind turbines, okay? So wind turbines, big windmills, right? Use air, wind to turn them. No combustion again. So good in terms of carbon dioxide. You got to make sure you're in a windy location though if you're going to build a windmill, right? You want to be windy like all the time to make sure it's productive. So along oceans, Lake Michigan area, there's a lot, like Green Appleton area, you see a bunch. The Great Plains has a bunch. What else?
Hydroelectric.
Hydroelectric. We have a hydroelectric power plant in Wausau, right by the Whitewater kayak course. Okay, so if you're driving from like Marathon Park towards Kentucky Fried Chicken, you keep going and eventually the library's on your left. As that bridge you're going over, I think it's the first bridge, you're going over past Kentucky Fried Chicken, there's a hydroelectric dam right there that produces electricity. What else?
So, wherever that place is by the junior high, where there's all the like electric stuff.
Oh, I think I know what you're talking about. Like right on the corner, kind of?
Yeah.
That's not a production, that's just a transmission. It's they got a bunch of transformers there. It's just a distribution center. They don't actually like make it there. Nuclear is the one that hadn't been mentioned yet. Okay, so nuclear power, we take uranium and cut it in half and it releases energy. And it creates steam, which produces electricity. Also, not combustion. Now, a lot of times people see nuclear power plants and they see these big towers and they see all this smoke coming out of it. Just to clarify, that's not smoke, that's steam. It's water vapor, so there's no combustion. It's converting nuclear energy into steam, which produces electricity. What's not great about nuclear power?
You can't test it.
What's that? the waste, right, the nuclear waste or the radiation that could be associated with it. There's been some accidents historically with nuclear power plants. Relatively they're safe, but we have long-term storage that we have to worry about. In Spain, how do we make electricity? What's the number one way, do you know?
No.
No. I know in France, nuclear is a big one.
Yes, I think so.
In Spain it is too. So in like some of our in European countries, sometimes, not all, they use a lot more nuclear power than we do. In Wisconsin, we used to have four nuclear power plants. One is on the University of Madison, is more of a research reactor. There's one in like just north of Two Rivers called Point Beach. That one's still operational. Just north of that is Kewanee, I think it was. They shut that one down about a decade ago. We still have armed guards on site to store and protect the nuclear waste so people don't steal it and make dirty bombs. And then there used to be one in La Crosse that went down, I'm guessing like 2 decades ago. Okay, so we do have some of those in Wisconsin, but there have been some accidents on Chernobyl, 3 Mile Island, and there was a tsunami in Japan that affected us. So there is some issues with those, but again, in terms of carbon dioxide, it's good for carbon dioxide because it doesn't produce that waste. Okay, that's a good stopping point. We'll see you guys tomorrow.